All right. I figure I'll go ahead and start, but you guys can keep, that's way too loud. Check, 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 yada, yada, blah, blah, blah. Is that, there we go. This is informal. You keep eating. Come down here while I'm talking. It doesn't bother me. But I'm mainly thinking I should start just so you guys are doing a meeting afterwards. Some of you don't want to be here that long. All right. For those of you that don't know, my name's Adam Beehler, and my title's physics lecture demonstrator. Actually, it's lecture demonstration.
Physics school demonstrator.
Oh. They wouldn't let me put that in there. No, I'm just... Lecture demonstration specialist. That's closer, yes. So that means I do demos. So we're going to do demos. Yes, Loriana refers to me as a fizzard. She just turned 11, and we just had a party yesterday on 11/11/11 for her with the Hogwarts theme. So we gave her an invite and everything. We made her a wand. It's official. You're a wizard now, right? What? We had a sorting hat and everything. Of course, everybody wants Gryffindor.
Ignore Dad spell.
Yeah, probably. Leave me alone. I'm with my friends. No, she's not there yet. So today, for Science Day, I chose electricity as the theme. So that's what you get.
Really?
Yep. This is the theme, yeah. If you guys have questions or comments throughout, let's do it. And we'll go till we've had enough. You or me. So some of you will know. This is fundamental. And some, hopefully, we'll walk through it and help us understand and make some connections between electricity and how it goes together. I'll start with static electricity. And how many types of static electricity are there? 4. What are they?
How many what?
I'll rephrase it since I didn't think the first question would stump you quite so fast, this group. How many types of charges are there? 2. And they are?
Positive, negative.
Are you positive? I'm half a joke, half serious.
Yes.
Are you positive?
Negative.
Are you made up of positive charges? Do you contain positive charges? Yes. Do you contain negative charges? Yes, but they're in balance. We call that neutral. Yeah. The charges, that's their source from atoms, if you forgot. The protons in the nucleus are charged positively and electrons negatively, and that's where all charges come from. So, I'm going to charge up something. Take these ping pong balls, rub them with this fur, and whenever you separate two materials, generally one has a greater affinity for electrons and the other less. And so in this case, the ping pong balls have a greater affinity. They grabbed more electrons. So they are now charged net negative. They have more negatives than positive. And so we say it's charged negatively. And what do negative charges do? Repel. They don't like each other. Positive charges don't like each other either. So same charges repel, like charges will attract. We can show that. How would you get the charge off? Say again?
Get a shock from it.
Shotgun? Huh?
Shock. Get a shock from it.
Oh, okay. I figured it wasn't a shotgun, but Yeah, I heard it and felt.
Work, you wouldn't have anything left though.
Is charge coming off?
Yeah, looks like it.
Slowly. This would be more effective. Can anybody tell me why? Because I made it greasy. Greasy gravy, go for guts. Okay, your quick review primer to help understand why that worked, so that we can make connections. I'm going to take the hair and a rubber rod. Rubber likes electrons like the plastic, so this becomes negative. Transfer the charge to this electroscope. The electrons spread out as much as they can because they don't like each other. It repels, you can see that. It's charged. If I take a metal rod and touch the electroscope, what do you expect to happen? They'll discharge. That excess of electrons now have a path. Let's see. Yes. So we call this a conductor. Metals are conductors. Or all. So I'll just go with most. Then I charge it again. Plastic. What do you expect? You're right. So we call it again. Insulator. Insulators don't allow charge to flow, move across them freely. This part was touching, and so some charge went to it. Just like if I just touch one part of the ping pong ball, that charge came off, but the rest of the charge isn't free to flow around the ping pong ball and into me, because it's an insulator. How about wood? Who thinks it's an insulator? Conductor, any takers? This has been in the back here for decades. Does that help you?
Yeah.
This was higher up. All right. I would never trust my life to wood. Wood's it's somewhere in between. It's not as good as a metal conductor, but it's not as insulating as plastic. So it can conduct electricity, especially if it had more moisture content. So that's insulator and conductors. You see why that didn't charge or discharge? Say again? I was making noise.
That's why I like it in trees.
No, well, they're higher up, so it's easier to reach, and the electric field is stronger. But yes, it's more likely to strike a conductor than an insulator. It's trying to find a path through the ground, and that's the easiest path for it. Let's do this one. You want to amaze your friends with the power of electricity instead of just doing ping pong balls. Here's a couple you could do at home. You take a 2x4 and question, is this positive or negative? Good. See, you guys are quick. It's neutral. Again, it still has positives and negatives. They're just in balance. So I'm going to charge up the rod. It's negative. Bring it near the 2x4, but not touching. And the negative rod seems to attract the 2x4, which isn't charged. Explain what's happening. What's that, Eric? That last thing you just said? Yeah, we'll simplify it for now. The negative charges in the wood want to go away because they're repelled, and the positives attract. So this becomes what we call polarized or induced, temporarily charged. And so there's a temporary attraction. When I remove the rod, they go back to their normal orientation. They just kind of rotate. The positives kind of get shoved one way and the negatives the other. And that's what we do for the public, because you don't all have dead cat lying around and a rubber rod, so I hope you don't rub your cat. But try any two materials. Take your wool sweater off. That'll be charged, and maybe it'll work. So you separate them, bring it near, and let's see. Yes, that'll work. And it looks like a really strong force, which it can be, but you put it on a 2x4 with a torque. See, force is over here, over a moment arm, lever away. Ooh. You can rotate a big 2x4, even though this is massive. You don't need much force to get it to turn, and we use that electrostatic force to do that. You guys have done this before with balloons. How many have rubbed a balloon on your head? Never, Catherine?
Always. Does it every morning when she wakes up.
So, let's do it. What do you do with the balloon after you rub it on your hair? Is the wall charged? Neutral, so it polarizes it and sticks to it. Thought I was going to make one. I was ready for the pop earlier, not then. I'll just stop there. Let's see. Well, it's not charged yet. That was your control. There we go. While that's up there for just a bit, you guys can try this at home. If you roll tape off of this, gets charged because I separated it from the roll. And if I do it a second time, this one gets charged as well. And do you think they're charged the same or opposite? So you expect them to do what when they get near each other? See, geniuses, geniuses. And it doesn't matter which side. You're right. So I don't know how they're charged, but they repel each other. They're the same charge. You can lay one flat. We're going to put them together. Discharge them. Now they're mostly neutral. And I'm going to separate these two. Now what? Yep. And this isn't some imaginary force at a distance through stickiness. This is the charge on them. Yeah. On one side, yeah, exactly. The sticky force. Yeah. And these are both the opposite charges. We know that now, but this one likes me, and this one likes me. They attract to me through that induction thing as well. It doesn't matter which charge they are. You can still attract. So attraction, you physicists, isn't conclusive to tell, because something could not be charged and something else charged and they could attract. But if they repel, then you know both have to be charged and the same. This is a special balloon though. That's why I chose this one. They can rocket balloons. Yeah. All right, who would like to get charged up? Volunteer time. Yeah, let's see. Who's got? Would you honor me?
Go for it, babe. Go up.
Oh!
She's got it.
Oh, we can both do it. We'll start with him. Come around here, please. Yeah, see this group, we got time. We can do it multiple times. Let's see. Let's put you like this.
All right.
If that's uncomfortable, is that too far away? There, okay. You done this before? You look pretty excited. So you know, don't let go and don't get too close? Okay. So a Van de Graaff generator, I plug it in, that runs a motor only. The belt inside there, it just turns the belt. And every time the belt comes off the roller, charges separate. And then kind of a reverse thing happens. It accumulates on the dome. He's touching the dome, so it's moving on to him too. It's the same charge, and so it's trying to spread out. He can feel it, I can tell. Can you ruffle your hair? And it takes a while to build up, but it's working on it. I don't see it sticking up too much yet. But he can definitely feel that, I'm sure. Oh, now it's starting to... It's this side, so... Can you see yourself? I couldn't hear you. Say again.
Explaining why?
You can let go now. Yeah, for this group especially. Want to give it a go? And I'll reiterate them with her because she looks like this is less familiar. This is charging up, and that's where we're going to head after this demonstration. Actually, you went a little further back, maybe there, because I don't want to hurt you. So, okay, you can touch it now. Charge is accumulating, lots of charge, and it's going to accumulate on her. It's trying to find a way to ground, to neutralize itself, so it can balance the charges. If she provides a path by touching this or getting too close, or me touching her, which I won't do, then it will go. All that charge on you will dissipate, and it hurts her. Not bad, but most people don't like it, and it's safe. And if she lets go, this keeps charging, but she doesn't. And so there's a difference in potential voltage, and that could cause a spark. Actually, it will. And that's kind of uncomfortable too. So as long as you don't get too close to here and don't let go, it shouldn't be a problem at all.
Okay.
Yeah, you can do it.
The person touching that would touch fingers and then you can see how far you can make it around.
So we'll get this in the Van de Graaff. The belt goes by some combs, some conductors that aren't touching, and it works through this induction process too. It like ionizes the air, starts inducing stuff, polarizes it, and that charge goes off. It's fun inside, but the whole reason that produces charge is through just separating the belt off the roller. All right, give us a shake. It's starting to work. Do you have a camera, sir? Now's your chance.
Just wash my head.
So, if you ever feel like this outside and it looks cloudy, take cover. Seriously, if you feel like that, yeah, lightning's imminent.
That's a good sign.
So we'll let him get a picture and then we'll free you. Don't get too close. I mean, never mind, zoom in. Did it work? All right, I'll free you. Don't let go yet. So now we're going to watch. The hair's still standing up because the charge doesn't have anywhere to go yet. But it slowly dissipates off of you. You can let go now. It won't zap you because it's not charging up anymore.
Yes, but you will zap it.
When you hit the floor, you'll feel a very little one. Did you hear that? Yeah. And now you're safe. If you don't have brave volunteers, you can try pie plates. Hey, Liliana, would you be so kind as to grab the ones that went up front? And packing peanuts are fun. These aren't physically touching it. And they're separated by the plastic. Yet, here goes. This one goes faster, so unless you don't want to be missing it. Ow. Thanks, Loriana. Now let's teach you about lightning rods. Why do you put a lightning rod on your house?
Create a pathway.
Create a pathway to the ground when it strikes it. Any other takers? To attract lightning?
It allows the air to ionize.
It does what? Because it has a point?
It allows the air to ionize.
It allows the air to ionize because it has a point. Three great theories. I've heard all three. So let's try it. Well, I guess, I don't have to talk over this. Water particles, molecules, are what cause the charge. All that rubbing and separating in the clouds is most of the charge accumulation. It induces or polarizes charge in the ground, and if it's a big enough difference, potential difference voltage, whammo, lightning, path to ground. So we're going to store up charge, and this is connected to ground. So we can draw some sparks. Maybe. So I can draw some pretty big ones. That's what I didn't want to happen to you. Here's a sharp point, my lightning rod. All you have to do is put it in the vicinity. If I put it on the house, that's all I can make. The sharp UN, the sharp point, ionizes the air around it because it has a high electric field. You physicists, it's a sharp radius, creates a high electric field, voltage per space. And that ionizes the air around it, which is conductive and allows the charge to bleed off. So it can't accumulate to its highest charge. And so it's less likely to get struck in the first place. That's the real reason of a lightning rod. Yes, if it strikes it, it can help channel it around your house instead of through your appliance. But it's to try to eliminate being struck in the first place. What? Oh, you can see the force, yeah. There's an actual, physical force there. Another way to do this, we can do it with the fur. You can do this with the people too, but it kind of disturbs them sometimes, so I don't do it. Charges up. Bring the lightning rod near and charge back up. Even in this area, just ionizes, allows a conductive path, and the charge on there can bleed off. So I can actually touch it with this, and I'm not getting shocked. But I would if I went this way. That's fine, but it's not the best thing that I enjoy all the time. Any conductive little tip would work. Actually, the biggest issue for me with electrostatic demos is worrying about scratches and nicks and dings and sharp edges because it won't store up the charge because it keeps bleeding off. So I need to keep this smooth and not have any scratches and gouges and sharp points. A kid last second session today had a coat, and I think it was a zipper. You could hear the corona discharge off the sharp points, and so his hair wasn't going up. I had him take his jacket off, and at least then it worked. So if you're trying to eliminate charge buildup, but if you want it, you got to get rid of it. Show you guys this one. Do it here. I know you don't all.
If you're like, because they say don't carry like a metal ladder out during a thunderstorm, wouldn't that do the same? Is it because it's not grounded? Well,
Because it's conductive, and so it's an easier path to ground, and a ladder usually goes up higher than you are, so it's more likely to get struck,
right.
and you'd be touching it. That's why. If your ladder had a whole bunch of sharp points on it, it might help. Yeah, it could. Now granted, it's still a conductor and it's higher up. And so if that's still the easiest way to ground, it'll strike it.
Is it also that the charge difference is going to be greater for being out in the storm as opposed to having the difference between charges? Is there going to be a bigger potential there?
Because of the ladder? Or the...
Because of the storm moving across and creating the...
Oh yeah, that is what creates the potential difference in the build of charge. Yeah, no, that is, the more likely it's to strike, yes. Or the closer it is. Yeah, just think of 100,000 volts across this distance, or this distance, which is more likely to spark? This one. And that's why a tree is closer, ladders closer, golf clubs closer. So the best thing to do, other than taking cover, but if you're out in the middle of the field, lie down, flat, get as low and away from it as you can, not near trees. Even if you're not near a tree and it strikes the tree, it can go through the ground into you.
Together,
So,
like this, rather than like this, because you keep the potential down if they're together.
that's the idea of the bird on the high wire. They don't get electrocuted at that high voltage because their feet are like this close apart. And so the difference in voltage from this foot to that foot isn't large enough to like electrocute them. But if we grab a hold of it, the difference from one side to another through us could be enough to electrocute us. And so, yeah, if you're closer together, then they're going to be at the same potential. She could let go of the dome once I turned it off because neither was going to get to a higher potential. You were at the same potential, same amount of charge. And so current cannot flow unless there's a difference of voltage to give it a push. This is I know you all don't have your own Van de Graaff, but you can. The Fun Fly stick is a toy you can buy for like $30 or less. And there's a mini little Van de Graaff generator in here. You take it apart, it's a rubber band. Goes around, battery-powered motor. And so it charges up this stick and you can do the same things. This is some really light Mylar. It's conductive, so you charge up the Van de Graaff, let it touch the Van de Graaff, it gets charged, and now they're the same charge, and you can act like you're levitating, because they repel. Yes. No, Leviosa, not Leviosa. Actually, yes, I did just record that. Assuming I hit the button right. This is good. What happens if I bring my hand near? What do you think? It'll attract to it because it polarizes it, then it'll touch, neutralize, and it falls back down, touches that, whoop, and then back to me. So sometimes you can get a little game going. It's all twisted now. You can have different. This works as long as it's conductive and extremely light, because this isn't, the most powerful thing. But it's fun. The Fun Fly stick. I think they even now make a clear version. I got to get one. All right. It's a magical creature. Must have it. There's plans on the web you can make them out of with a pop can, like as the top dome. I have the parts for 2 of them over here. I just haven't finished them yet. All right. What else? Let's do. Okay, we're storing charge. You guys can appreciate what a capacitor is, so I'll do this for you. A capacitor can hold charge, and all it is 2 conductors separated by an insulator. That's it. It can hold charge. You can put charge onto it like this, and it'll hold it. That one's not as fun, so I'm going to use this one. I didn't do this for any other group today. You guys should appreciate it. There's demos that are good, there's demos that are effective.
Is that capacitor there or something? Is there a holder that has to suck it all in?
No. Theoretically, though, it can. And I have some dielectric oil that I can, if I get the plates really close together and put like 4,000 volts on it, I can get the oil to get sucked in about that much. So you can see the effect, but yeah, it's a small effect. Was that your class, Thomas? You saw that with the full? Proof. Okay, I'm going to draw the charge off the Van de Graaff and put it on that conductor. Here's the insulator separating and the other conductor on the inside. Those conductors can't touch each other. I need to put this one on the top.
Aren't they both touching the metal base?
No.
Oh, sorry. Okay, thanks. I didn't see that. It had bottom end.
So let's turn it on. Interlude music. Charge stores in there. It needs a path to get from one conductor to the other, inside to outside. So I'm going to short it out like this, touch the outside to the inside. You ready? Yeah. Now, if any of you are thinking, whoop-de-doo, I dare you to touch that. It's a small spark, but hopefully most of you at least could hear it. Well, let's do it again. All right. Now, I can touch that one. Don't need this. Don't need this. I can touch this. You can take it apart. I can touch this. I can even touch these. I love that. Could you hear it? It's the dissectable Leyden jar. Guy's last name. But yeah, it's a capacitor. That just freaks me out. People still aren't fully sure, but they think it's most of the charge is stored on the surface of the insulator material, the dielectric.
Was the charge not completed?
Yes. Okay. If it was stored on me and I touched it, where do you think the charge would go? Yeah, but I didn't get shocked. I am touching this, didn't get shocked. How's it different than those? And charge can't flow. So I have messed with it. If I went like this, it doesn't work. The more I touch it, the less it works. But yeah, if I just handle it a little, most of the charge is still there. It's cool. This is a demo. Yeah, I have a rating system. The demo is zesty and effective, like this. And I have effective but boring. Still works. We're going to use it. But, it shows the point. You got to do it, but it's kind of boring. And then there's the and boring. And then I have another level below that. Physicists like it. Take your pick where you put this one, but most people don't appreciate this one. That's why I show it to most of you are physicists. So you can fully appreciate this one. That's kind of cool. All right. This is a Leyden jar, a capacitor. Water's inside and a bolt. That's the inner conductor, aluminum foil, the outer conductor separated by the insulator, the plastic. Let's charge it up. And we're going to start moving charge now, making circuits. I need you guys to be the circuit. If you're willing, come down and make a circle. Hold pinkies with your neighbor. Right here. blow it up. Is that what you just said? Oh, heck.
Is this back to the...
I don't need this. So I'm going to charge it up. That's not a circle. All right. Can I get through? Thanks. All right. Why don't you guys go that way, and you two come together? Great. So things we can teach with this is holding charge, and you now know it wants to get from the two conductors. It needs a path. So that's you, so don't let go. Because if there's a break, it can't see the two sides, it won't flow. Who would like to be the switch? Sold? So I'm going to hold your pinky, and the only way it can get from the outer aluminum foil that I'm touching is if he touches the bolt in the top. So is everybody connected?
How do we know when it's going to flow?
You're gonna feel it.
As soon as the switch is closed, right?
Yeah.
Okay. Whenever you're ready, kind sir. Do you want to do it again? Yes. If you do, stay here.
Stay with the electric fence.
If you'd like to do it again, I'll do it.
Oh, everyone's listening.
Okay.
That was awesome.
If it was just two people, would you still want to do it again?
Probably not.
Why?
Not enough resistance.
Well, less resistance. Less resistance, more current can flow. The voltage is trying to put. So you would feel even more.
Check in.
Let's see if it's discharged. Yeah. I had a friend at Colorado State University. He swore that it was discharged, and people weren't sure because they were all intrepid. And he goes, "Oh, I'll show you." And instead of just testing it or like that, yeah, he touches it to his tongue. Well, needless to say, it wasn't. It was fully charged, and he said his neck muscles were sore for like 3 weeks. He wasn't, no. A guy in Little Shop. I don't even remember his name now, but. Okay, things you guys can learn from that. One, I saw you all jump and or yell at the same time. That tells me once the switch was closed, current was flowing almost everywhere instantaneously. It kind of works like this. You make this charge try to move, then over here, as soon as you... Some balls are fatter than others, so I'll do it this way. You push the ball in, and those almost immediately come out. But the individual charges are not whizzing around at the speed of light. They don't move relatively fast. But the wave can. You turn on a switch, it doesn't take time to watch the light bulbs light up. As soon as you close the switch, charges are moving everywhere. That's why you all jumped about the same time. And second, you all felt exactly the same thing. Okay, see where those went? Gonna need those later. Thanks, I might as well find them now. The other thing, that was a series circuit, one continuous loop. And so it was the same amount of charge. What had to get through one person made it to the next person. And so we all felt the same thing. A lot of people are really afraid to be the switch because they think it's going to hurt more. You all felt the same thing as the switch. So let's charge up something else. This capacitor. Who wants to touch this one?
Are we grabbing some more one of these?
For you physicists out there, this one is 32 joules. I'm not touching it. So I'm going to connect it to this power supply. It's at 4,000 volts. Turn on the power supply. Charge is going into the capacitor. It's storing it. And internally in there, it's just a bunch of conductors separated by an insulator. Turn it off, unplug it, and let's give it a path. Ready?
Whoa!
That's why we don't touch it. Let's do it again. That's long enough. You ready? Did you get it, Loriana? No. One more time. I'll count to 3, and when I say 3, I'm going to try to make contact. So push the button down before it. It's so fast, though, I'm not sure you'll get it, Loriana. All right. 1, 2, 3. So capacitors can store the charge so we can use them, and they can pack a wallop. Let's do the Jacob's ladder. This, we're going to use a transformer. It steps the voltage. This is 120 volts. This steps it up to 12,000 volts, and it is on the 2 sides of the copper wire that's not touching. But if it's a big enough voltage, it breaks down the air like the Van de Graaff and will spark. Let's do it. Every proper mad scientist, oxymoron, needs one of these. So it breaks down the air and completes the circuit. Charge flows through. What do you think it does to the air? It ionizes it, makes it conductive, so it's easier to go. And what else do you think it does to the air? Would you like to touch this? Yeah. One reason is because it would burn you. It's hot, and hot air rises, so it stays with the hot ionized air. It's easier for it to conduct. Until it gets too far apart, it can't jump anymore.
Is all of it being ionized, having both oxygen and nitrogen?
Yes. It's been a while since I looked at a spectrum of this.
That's what I was going to ask. When we see anything, if we looked at it with grading glasses, would it be different?
I will, you know where they're at? Do you remember?
I'll go look. Grading, traction grading.
Turn right, go down that aisle, up on your right on the top. What Ennis is going to get some diffraction gratings so that we can break this light up into its component colors to see what gases are being ionized. Let's while she's passing those out. Yeah.
The sparks here, they look different from what you see with the Van de Graaff.
That's an excellent question. These are both sparks through air, so why does it look different colors? Yes. Ennis might help me, but my theory is we have different amounts of charge going through. This is probably, thank you, about 200 to 300,000 volts, but the current's low. This is 12,000 volts, but the current is lethal. And so different pumps. Each atom with the electrons going around it in different levels, when you ionize something, the electrons can either be stripped.
It's pretty cool.
Oh. If you give electrons energy, they change where they're at. Eventually they come back to where they were at, and when they come back, they have to give up that energy in the form of light, whether it's visible or not. Well, depending how far they jump back down, depends on the color of light that comes off. And different atoms have different jump levels. And the same atom can make different jumps. So my guess is different energies, you're affecting different electrons, and so even for the same element, gas, like nitrogen, which is most common, you may be getting different jumps, and thus different color mixing in. Maybe that's why that looks a different color than this. This does include copper, too, a bit, because where that one doesn't. Let's turn it on and see. We'll probably be better with all lights off. You know what? I should have done that after I plugged it in.
You want this door closed?
Oh, looking over here, it shouldn't matter. You can. Oh, yeah. You're blinded with science. So this should look like a continuous spectrum, I would think. All colors?
Yes.
But if it's just gases,
Pretty continuous.
it's mostly continuous. Because it's hot and glowing in mostly all wavelengths. Now, if you look closely, I can see some yellow little specks.
Yeah.
I'm guessing that's sodium.
Yeah.
But yeah, I can't really pick out individual elements.
No. But I agree with you. I think that is sodium. It's pretty
The sparkles are very just where it started, so there's a little island there. Seems to be like two distinct.
Yeah, two distinct wavelengths.
Yeah.
Yeah.
Gonna let the air currents flow down a little. Maybe it'll go up a little smoother. Not necessarily. Any conclusions other than what we said? That's all I can tell. All right. Cool. Thanks, Ennis.
That's great. And even that LED thing that you have is a nice illustration. That one,
Here.
not so much.
That-
Although, yeah,
that one?
it's still good.
Quite like those nice spikes.
Yeah.
Oh, yeah.
The wavelengths are more discrete than they are in the continuum.
Off of this?
Yeah.
I don't have to walk over there.
Which is really kind of. And what I mean by discrete is
Oh, yeah.
the reds are reds, the blues are blues, the greens are greens, as opposed to this continuum bone that gives you the wave, all the wavelengths. That's really neat. I like that a lot.
Excellent.
What do you have in that flashlight?
They're just white LEDs.
But white LEDs, that means they should be across the continuum.
Which, yeah, I think it's continuous, isn't it?
Yeah, okay. But still, it's brighter in blue than,
There you go.
so that's how they make the white.
I would like to ask John a question. When would you like me to? Because I'll end any time.
You know what? We're having fun.
Okay. I just didn't want to.
I guess whenever I leave, you
Okay, because I have more, obviously. But, okay. Well, let's do some more then.
we got to go somewhere else. We can't do our meeting.
What? Yeah, I'm going to do that one next. If you want more food, come on down.
That's the one I couldn't pick out.
Doing more light stuff?
Yeah, keep them for a moment. Because you could look at them through this. This would be continuous, but I got an LED here.
Okay.
So we could look at that. Yeah. All right, I'll regroup here. That one, and then into magnetism and wrap things up. Okay. Okay, so you send it through air. We've been doing lots of sparks, or through us. You send electricity through anything, it'll have some resistance and will cause heat. And the skinnier your line, like this skinny piece of wire, that has a lot of resistance. It's hard to shove the charges through. The voltage is the push. The current is the charges going through. And so we're going to force them through there. It'll heat up and glow, just like the air does. And that's how incandescent light bulbs give us light. Shove charges through, gets resistance, heats up, glows. This also, I'm stalling so you can all see when they get their food, you're fine, is how a fuse works. You can build this to rate it at, say, 10 amps of current. And if more than 10 amps go through it, it burns apart. breaks the circuit and current can no longer flow, hopefully in time that has saved your device. A lot of the public think, oh, my 10 amp fuse blew. Well, I'm going to put a 15 amp in there to protect it. That'll be better. Now, that means it won't open until it reaches 15 amps of current, which might be too late.
Or how about this one, people who say, oh, we'll put a penny in.
Oh, yes. We'll just put a penny in to complete the connection. Yeah, it'll never blow. You're right. Until your TV blows. That's
Did the history of like the fuse blow come from an old fuse that actually popped out? That physically popped out?
and not reusable, yes. Yeah, it would. Now, yeah. Some would just be wires that would melt, and others would physically, they were contained, in my impression. They'd heat up, the pressure would blow it out.
And there's some fuses that are used that way at David Belmont Observatory. This is a facility that was built in the 1930s. And they have these enormously long fuses. So usually there are little bombs, and we've already seen it's not so good, but it's what they use. And when the fuse blows, it actually blows apart.
I need to go now.
Okay.
Okay. Okay, thanks. Our meeting starts at 7 tonight.
Okay.
You're in the theory recording.
Just turn it off. Turn that around. Okay. Got it. Thanks.
Love ya.
So this one should glow, and we'll see if it's enough to break it. We might as well turn the lights off when we do it, and you can look at it through your glasses too to see the spectrum. It's emitting, it's a hot body. So I expect mostly a continuous spectrum, all wavelengths. We'll see. I haven't looked at this before like this, so. Are you ready? Those that want to see it with the glasses? Oh yeah, safety. I left it unplugged lest some unsuspecting, interested physics person came up here, flipped the switch, and electrocuted themselves. All right. Okay, here we go. I'll count to 3 and turn it on, and then you should have a couple seconds. Ready? Good, that one worked well. Steel. Yeah, I just found some scrap steel wire.
And how thin is it?
Millimeter-ish.
No.
Yeah. Based on the material, its conductivity, its thickness, and its length, all affect its resistance. And so you can play around with wires if your power supply can handle it. Say this was longer. That'd have more resistance, less current would flow, and it might glow but not burn out. Or
Why? Some extension cords you can use for some purposes.
yes. Actually, the last Tesla coil I had, if the extension cord was too long, it wouldn't work. Too much resistance, it wasn't getting enough power to the device.
Well, what about the other way? Way too hot?
Yes. Yeah, because I think these are all clear that I hope that you shove electricity through it, it's going to get hot. All right. I think Aaron's new favorite demo. Let's do it.
I do love that.
Aluminum slug, copper pipe, hollow. You drop it down, you expect what to happen? Yeah. Forgot where I stuck the magnet. This is a magnet. Thank you, though. Is copper magnetic? No. Steel is. So when you drop it down, it doesn't stick to the copper. It's still falling.
I do like your little.
I'll show you. Boom. There it is. It took that long. And we're going to do the next demos will help explain this. So how long you can see this film as it goes by. It has nickel colloidally suspended in a thin film. It's like iron filings that are free to move, and they align themselves and change whether it looks dark or light. So you can kind of see when a magnetic field's dropping by it. I'll do it again so you can notice that while the projector's coming on.
That film, is it something that you would normally buy flat?
Yeah, it's a sheet, flexible sheet.
So could you use it to display magnetic field lines?
Yes, if it's right on the magnet. All right. This is what the paper's for. Because you can't see anything without the paper. That helps. Here goes. This is what's happening.
It actually flips over halfway.
Yeah, the metal clamp right here, it's attracted to it. And so it kind of comes to that side, rotates and keeps going. Wouldn't do that at all if this metal clamp wasn't near it.
Where does this demo race?
Oh, this is zesty. In my mind. Effective and zesty. Now let's understand this a little more. We'll come do it again. All right, some of you know this, some of you don't. Let's review. This is a coil of wire. Yeah, help yourself. We've been coming down anytime. Nah. Coil of wire. This is called a galvanometer. It's a sensitive ammeter. It'll move if current's flowing through it. Is current flowing? No. This is a magnet. This is a TV. Magnets have magnetic fields. I know you guys know this, but this is my favorite way to show it, even though it's not technically accurate. It's more fun. So this has a magnetic field going around it. See? Yeah, this is obsolete CRT, cathode ray tube.
Try to do this with your LCD TV.
I haven't yet because I don't have one. I do not encourage you to try it. But if you do, will you let me know what happened? Your neighbors. Yeah. So there's magnetic fields around magnets. You guys know that. This coil of wire can feel the magnetic field. It's in it. But is current flowing? How about now? 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 Now?
Yes. 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 Yes.
Yeah, it's the motion that matters. It's not the magnetic field, it's a change in magnetic field. Increase, decrease. That's when current flows. Generator. It doesn't matter whether this is moving or this is moving. There's a relativity demo. That really is a relativity demo. Einstein worked that one out. Or both. So all generators are pretty much, there's a magnet and a coil of wire somewhere moving with respect to create electricity. Point is, moving, changing magnetic fields cause charges to flow. So we have a moving magnet over here. As it falls, boom, this conductor feels a change, increase and decrease in magnetic field. And so it causes the charges that are already here to start moving. Eddy currents, they're called. That's step one. You with me? Well, the second key is, these TVs, if you didn't know, shoot electrons from the back to the front. A charged particle. They hit the phosphors and make them glow, and that's what we see. So, magnetic fields exert forces on moving charges. This magnet isn't moving, the magnetic field's not changing, but charges are moving near it. And in that magnetic field, it feels a force. That's the little Lorentz force for you physics majors. And so you can deflect and exert forces on moving charges. Now follow me, you guys should better. The moving magnet causes charges to move in the copper. But that magnet still has a magnetic field that exerts a force on those moving charges. And so it pushes on it. And anything that pushes on something pushes back, Newton's third law. And so it retards the falling motion of the magnet. Let's do it again. One more time. Now that you can really appreciate it. Seen that Simpsons episode where the subs are coming in and the scientist guy, he's up there teaching with the like popcorn kid thing. Can I try it? No, not until you can fully appreciate it on as many levels as me. All right. The metal melting thing. Oh, this thing?
Yeah.
All right. All right.
Did you ever different metals?
All right. Yeah, extra or there's
As extra, and lead, so.
Yeah, also with the gradient glasses, shouldn't we see peak wavelength in the black body?
And if you look in slow motion,
Yes.
you will see the rate of exchange is function
I'm going to start longer and see if it just glows before it breaks. It might not glow at all. I might have to shorten it, but what the heck?
Am I supposed to be watching this with these on?
This is direct.
So like, yeah.
It's plugged into the wall, but there's a converter in there.
It's basically the same thing that the piece.
Should, yeah. Well, I can leave it up. So you want the lights down with food glasses for it? Ready? Yeah, so that one, it doesn't burn away right away. What happens is it oxidizes the air, and the steel actually goes away, and it gets thinner and thinner and thinner, which is runaway actually, because the thinner it gets, the more resistance it is. It's trying to shove more current through it, heats up even more, gets thinner, and eventually this will eventually break. Shall we shorten it so it break? Oh, yeah. So me, I don't see much blue in this.
I don't either, but I did before. So,
It was hotter before because it burnt in half. So this one, yeah, you can see the peak wavelength roughly as an average of those, so yellow. It's shifted more like in the yellow because I don't see any blue in that. I can't. Let's shorten it. That should make it be hotter. And we should see blue. I just might not be able to touch it for a moment. So I'll stall for a moment. Any of you guys bought these flashlights? This works just like this. You don't need batteries. Here's the magnet, here's the coil. It only produces light when it has a change in magnetic field. You stop, no current flows. Glad you guys came. Thanks for helping me. So, you don't want to walk around like this though, so what do they do? Yeah, flip it. And now, instead of going through the light bulb through the coil is connected to the capacitor. You don't get light, but you store charge in the capacitor. And just so you don't have to sit here and watch me do this for a minute. Now connect it, and the capacitor is going through the light bulb, and you get light for a while. So you don't need batteries. It's a generator. It's for your spectrum, it is. Yes. I want to see it next month. Do it and show me. This one doesn't have a capacitor. It's not even an LED. But it does have a magnet next to a coil of wire. I would give this to Loriana, my daughter, when we'd go camping. because I didn't have to replace the batteries when she'd leave it on all night. And I knew where she was at. When. And she thought it was cool. You can do the same thing with a drill. I took this one, took the battery out, and connected up to the leads in there. And run it backwards. Because there's a magnet and a coil of wire in there. A generator and a motor are the same thing, just depends on which direction you're going. If you're producing electricity, generator. Go the other way, motor. Faster you go, the greater the change, more current flows. That's a 12-volt automotive bulb, I think. All right, let's see this. Okay. Let's see, maybe that short? Ready?
A little bit.
That's the spot that wore the thinnest first. And I don't know if you were watching it right at that spot, but I saw some blue in the spectrum at that point as it got hotter. And the peak wavelength did shift. Cool. Let's see. Where are we at here? Oh, you guys will like these, I think. Here's a battery, a magnet, a nail, and I just have a piece of wire. So this is a magnet, and I just stuck a nail to it. I made this little vein just so you can see if it's moving or not. So that's connecting to one side of the battery, and if they're all connected, so if I complete the circuit with the wire, I was afraid of. Yeah. And you're like, so what, Adam? While I fiddle with it, and it worked this morning, magnet exerts forces on moving charges. So as soon as I complete the circuit, charges are flowing, but then it pushes on those moving charges, pushes back, creates a torque, and this thing starts spinning. It's a motor. These are called homopolar motors. I've learned, though, it has to be nice and symmetrical and balanced, and little friction up here, or it doesn't go all the time. So I'm just twiddling and hoping I get lucky. Oh, bueno. So I got my own little commutator switch here as it spins around the wire. I'm just holding it against the side so it brushes up against it. Current flows, moving charges, pushed on by the magnetic field, and that little lever arm just on the radius of the magnet makes it spin. Another version there's some magnets on the bottom, and so it connects the circuit down to the bottom, but then same idea, the magnetic field pushes on those moving charges as they the magnets down there. I like this one better.
Is it AA battery?
Yep.
With a magnet base?
Yep.
And copper wire?
The hardest part of this is just making this so it's nice and symmetric and not too tight, too loose. I sanded the copper so it makes connection. I put a nut and two magnets there just for more area, raised it up a little. And so these are just acting like little brushes along the magnets part. Oh, you have to sand this part too, so it makes connection.
So does it matter which direction it's going first? Like, is there a preferred direction?
Depends on which way your magnets are facing, really. Well, and which direction the current's flowing. So yeah, you can get it to go the other way by flipping the battery over or the magnets or...
The reason I ask is because the magnets in the copper aren't interacting directly. The copper is not.
No. Correct. That you guys appreciate that. There's several cute versions of homopolar motors. You can YouTube them. But it's that same principle. And this isn't a homopolar motor, but here you go, Aaron. I love different ways of doing this Lenz's law stuff. These are two batteries out of hard drives. They're strong magnets. So instead of dropping the magnet down a conductor, let's drop the conductor through a magnetic field. Aluminum's a conductor too. It's lighter than this one, so it goes a little slower. Even though this is a better conductor, the weight factor. What do you expect to happen with this one?
What is it?
Copper with some slits cut in part of it.
Very slowly.
Solid.
It'll drop through.
Solid. Slits. Solid. Slits. What's going on there?
Can't maintain a loop for the circuit.
Right. Somebody let go of their pinky. Yeah, it's trying to induce currents in here, but there's not a path. They actually make little circles. It's the way the geometry works out with the change in magnetic field if you want to work this out in your math classes, in physics. So you can go fast, whoop, and then slow. If afterwards you want to come up, my favorite thing with this is just yank on it. The faster I move this, the greater the change, and the more it pushes and pulls. I can feel it tugging against me. Kind of fun.
With the cone looking you can't complete the circuit, there's still 8 loops in there.
Yes, and notice, when it gets to there, it's still not going this fast. So yes, there are some little, but it's a lot less. Good observation. So that's fun. Let's do, I got 2 more for you then, set up. The ring shooter. Now you can appreciate this one. Here's a coil of wire. I've got a switch down here that sends electricity through it. When electricity goes through it, it makes a magnetic field. This is iron, and so it gets magnetized and helps channel the magnetic field up and around. It magnetizes this adds to it, if you will, and so it makes the field stronger, if you will. Here's a coil of wire connected to a light bulb. These are not electrically connected. And I want you to see that this is the essence of a transformer. You send current through one coil, you can induce current in the second coil. I love that. It will even go through water. We have this one you can put in water. That's not the fun part. But here's an aluminum ring. Is aluminum magnetic? No. So this is not going to get repelled by the magnetic field, but it does get repelled. Changing magnetic field. It's AC current. Thank you, Thomas. Induces currents in here. And then you now know magnetic fields exert forces on moving currents, and so it pushes on it. That's the essence. This one has a slit. I expect you to guess what will happen now. Boring. Yes. You can adjust this too, and that changes the flux and strength of the field. Not as impressive. But at this distance, trial and error. It works best. But even better, liquid nitrogen. Most things, when they get cold, decrease their resistance, which allows what for the current? Yeah, that means more current can flow if it's able to. So, more current in this magnetic field, bigger force. I expect it to go higher.